Hi everyone, welcome to another ZX seminar. Today we have Leo Colisson of University of Amsterdam, who will be talking to us about some cryptography using ZX diagrams, or well, at least a part of that is done using ZX diagrams. Namely, all graph state verification protocols are composably secure. Please, Leo, take it away.
Thanks a lot for the introduction and invitation. So I will present this work, which is a joint work with Damian, Markham, and Yehia. So the title, all graph state verification protocols are composably secure. So what does it mean exactly? Well, we can just decompose it. So a graph state is a famous class of quantum state, which is basically made of plus state. So get 0 plus get 1. So in ZX calculus, I guess most of you know that they are represented this way. And then we can create a graph by applying a control Z operation between sets of qubits. And then at the end, the set of control Z operation that you apply will define a graph between your qubits, which is usually enough, which is enough to define a graph. So why do we bother about graph state? Well, this class encompasses many important states. For instance, bell pairs, TZ state, and many more states are all locally equivalent, at least to graph state, in the sense that once you have a graph state, you can obtain one of these states by performing a local operation, typically just Clifford. And graph states are the starting point of many protocols. For instance, in quantum teleportation, you usually start your protocol by saying, let's assume that we have a bell pair between the participant, and then let's teleport the state. But you have also a graph state involving anonymous transmission, in universal band quantum computing, and many more protocols. So the big question that we usually want to answer is how can we actually make sure that the parties start with such state that are honestly prepared. Like as I said before, many protocols start from let's assume that all parties share a state. How can we prepare this state? And so verification protocols are exactly here in order to fill this gap, in order to make sure that all parties share a state. And here, most of the time, we also care about security, in the sense that maybe the source is malicious, maybe some parties are malicious and may try to send different states, for instance, in order to implement a man-in-the-middle channel to intercept a quantum communication channel, or that kind of things. So in the following, by malicious, I will assume that an arbitrary coalition of parties may try to attack the protocol. And by the way, also I forgot to tell, but please feel free to interrupt me at any time if you have any question. And I'm also not sure if I can see the chat. So, all right. Now, in cryptography, there is an important notion of composable security. So what does it mean to be composable? So let's say that you consider a verification protocol. So at the end, you are sure that you prepare a state that has the expected shape. Are we still sure that when we use this state into other protocols, then the security of the new composed protocol is still a guarantee? So in cryptography, we have usually this level of security. So in gate-based security, we need to reprove the security of the final protocol whenever you take two protocols together and combine them into a new protocol. And then you have composable framework. So in this framework, you're also guaranteed that the protocol stays secure whenever you compose the protocol. So in sequential composable framework, then you can safely compose protocol sequentially, so one after the other. And in general composable frameworks, so then you can also compose them in parallel and in any arbitrary way. So in our case, we will actually focus on a general composable framework that is called abstract cryptography. And so the question that So the thing that we prove is that we can take any verification protocol that is secure in the game-based security framework, and then this protocol is actually secure in a general composable way. So in a sense, it can be safely used and in any protocol without weakening the security. So actually what we exactly prove is a bit different, like slightly different. So what we prove is that any graph state verification protocol can be turned into a composably secure protocol. So the protocol itself does not realize the functionality that we would like to implement. I will give a bit more detail on this in a few slides. So one might ask, okay, but I mean, is it just like a prem in our proof, or is it fundamental? And then we prove that it is actually optimal. So it means that if we want to prove a generic result that works for any arbitrary protocol, then we need to either adapt the protocol itself, so it's what we do in this first theorem, or we need to change the functionality, which is a way to define security in the abstract cryptography framework. And so we also, as a third result, we also prove that if we don't want to change the protocol at all, then the protocol is still composably secure, but with a functionality that is not as natural as the standard functionality that we would like to consider. So at that step, we're in a ZX seminar, and some of you might wonder why I'm even here. And it turns out that we use an essential tool in our method, proof method that is based on the scalable ZX calculus. And I think it's one of the first application of scalable ZX calculus to cryptography. And I've been unable at least to come up with this protocol without this tool. So I think it's a nice application. All right, so now let's me introduce a bit composable framework, so the abstract cryptography framework. So in, as I said before, in verification protocol, we have many parties. So here you can see the source, and the source will prepare, so in many protocol, the source will prepare a quantum state, and then you will do some testing, sometimes some amplification method to distill a better state. And at the end, all parties will either abort or send the output of a part of quantum state. So here I will represent a GZ state, which is a graph state using this Z spider and all these wires. All right, so now we expect this protocol to stay secure even if some parties are malicious, so either some parties or even the source, and all these parties may try to break this protocol. So in practice, we tend to model security using abstract cryptography using what we call a resource or a functionality. They are basically the same. And a resource is a kind of trusted party that will be in charge of distributing the graph state. So of course, in the real protocol, you will not have access to this trusted party, but then you will define security if you cannot distinguish this resource from the actual party. So in practice, we have this two world. So what we define as the ideal world, in which you have a resource that shares the state with all parties. So it means that here you can see, for instance, that if the source is malicious, she has no way to send a state that is not a GZ state, because this source just produces a GZ state and share this state with other parties. So in practice, this resource is slightly more complicated because we also allow parties to abort if they want, but except for abort, then this resource will just generate a GZ state or a graph state in general. And then in what we call the real world, then the parties will just interact as in the real protocol, so following the specification by sending messages between each others. And so now the goal is, so we'll say that this protocol is secure if it is impossible to make a distinction between these two words. So what do we mean exactly by this? So we'll define what we call a distinguisher. So the distinguisher will basically absorb all malicious parties inside, into a new entity that we call this distinguisher. And the distinguisher will be able to send the input and output to the party. So in this case, you have no input, you just have an output quantum state. And so in the real world, the distinguisher will be able to see the communication that happens in the real world. And then in the ideal world, it's a bit the same. So you will also take all the parties inside the distinguisher, all the malicious parties inside the distinguisher. But there is still, so right now you can easily distinguish these two words, because in this case you see messages that are exchanged depending on the protocol. And here you just see two quantum states sent to the distinguisher. So in order to avoid that, we will introduce, I forgot to say that this distinguisher is just supposed to output one bit, real or ideal, depending on which word is supposed to interact with. And then, so as I said before, in order to fake the communication that happens in the real world, we will introduce what we call a simulator, this orange box down there. And so this simulator will be in between the resource R and the distinguisher. The simulator will be in charge of faking all the interaction that happens in the real world. And intuitively, this, in some sense, this is a good definition of security, because if somehow you can do some sort of attack in the real world, like for instance, let's say that you manage to send a state that is different from a digit state, then you should also be able to apply the same attack in the ideal world. Otherwise, you could easily, you could easily distinguish the two worlds by just applying the attack and check if this attack succeeds. If it succeeds, then you are in the real world. Otherwise, you are in the ideal world. So that's the intuition behind this notion of security. And here you can see that the definition of the resource is important to have a proper notion of security. All right, so when we prove the security of the composable security of any protocol, then the major question is, how do you define the simulator? What simulator are you using? And here, if we want to consider any arbitrary protocol, we don't really know what the protocol is made of, because it's a black box proof that we want to write. So the most natural thing, and actually it's basically the only thing you can do, is to start by applying inside the simulator the protocol that the honest parties are doing. So this party, they will send some messages to the distinguisher. And at the end of the interaction, unless they abort, so if the distinguisher aborted, then you will be able to forward this message to the resource from the side of the simulator. And if there is no abort, then the simulator will just share a quantum state with the distinguisher. And now, right now, let's even consider a distinguisher that is behaving honestly, in the sense that the distinguisher just runs the honest protocol on their side. So in that case, you have basically a digit state that is shared between the distinguisher and the simulator. You also have a graph state that is shared between the honest parties and the simulator by via the resource. But of course, in the real world, at the end of the protocol, you will end up with a single state that will be shared between the honest parties and the distinguisher. So somehow we need to find a way to take the two quantum states, the one given by the resource and the one given by the distinguisher, and merge them into a single quantum state. So intuitively, what we would like to find is to find a map where you take two graph states. So here I just drew graph state like using this blue dashed line in order to represent a Control Z operation. So here you have two graph states, and you want to find an operation that basically works on the first half of the first graph state and on the second half of the second graph state in order to create a new copy of a single copy of a graph state. So more precisely, so this is like the rough picture that we would like to have. So let's say, for instance, that we can find a map question mark here that takes a graph state that is split between one part that will be given to the honest party and one part that will be intuitively given to the malicious parties. And then we want to apply this map to one copy of one graph state and another copy to another part of the other graph state, and at the end obtain this original graph G. So if you think for a second, sadly it is impossible to find such a map. Why? Because it will violate non-signaling. So I can write a diagrammatic proof here, but you can also formalize it using a more standard proof. Or you basically, let's say that instead of considering this graph G, you consider just a Bell pair here. Then if there exists such a map that can fuse or merge these two Bell pairs into a single one, then this map has no output so far. So it means that if you discard this map, then due to the property of non-signaling, then it means that it is equivalent to directly discard one input of one state and the other input of the the two parts of the Bell pairs. And so this thing is actually equivalent to identity density matrix, which is of course different to the Bell pair. So it means that without, if this box has no output, then it is impossible to merge these two states into a single one. So from now we are left with two options. Either we need to change the functionality, or we need to change the protocol. So I will start with the first option. So I will change the functionality, and then I will see how we can change the protocol later on, building on what we will do for this first option. So as I said before, it is impossible to find such a map. So the first thing that we can naturally try is to produce some sort of output from this box that will be run by the simulator at the end. And then this output, so if we redirect it to the right part, then intuitively it will be given to the distinguisher at the end, which is not what we want, because if we send another message, then the distinguisher can easily see, I mean, this will not be part of the protocol. It will be an extra message that will be usable by the distinguisher to know if they are in the real world or in the ideal world. So here instead, the most natural option is to say that this question mark box will send the output of the measurement to this ideal functionality. And then, so this ideal functionality, now they will have some measurement outcomes sent by this box, and then they will apply some map xi h here. And then at the end of this map, we expect that this quantum state that will be shared between this interface here and here is equal to a single copy of the graph state. So here you can see that I add a function f here. And in fact, this box will additionally check if the correction that we send from the simulator to this box here have some properties. So this is required in order to have a stronger security, because if you are allowed to apply anything here, then this box is not really considered as secure, because you can send any state you want. So I will argue why we need to take some precise function here, and why it is actually not decreasing the security in any way. All right, so here, for simplicity, I just reorder the boxes in a more circuit-like picture. So here I have these two states, I apply this box and then some correction, and then I create this state G. So you can see that this is easily doable in some cases, because this is very close to entanglement swapping. So in entanglement swapping, you have two Bell pairs, and then you want to merge them into a single Bell pair. Except that we want to do that for any state, and that we also want the correction to be on a single interface, namely the one of the malicious party. So for instance, if we consider Bell pairs again, then you have these two Bell pairs here, and then you can perform a Bell measurement that we represent in ZX using this thing where A and B are bits. And then, so you do this Bell measurement, then you do some correction here, and then anyone familiar with ZX will easily be able to check that this is actually indeed a single copy of our Bell pair. And we can also do that for other states, notably GZ states. So in the GZ state, so as I said before, it's simply a green spider connected with all output. And so what you can do is that you can measure all outcomes, all qubits in the plus or minus basis, except one qubit that you will keep for the first copy, and one qubit of the second copy that you will use together in order to perform a Bell measurement. And then again, if you are familiar with ZX calculus, then you can see that all these green nodes will basically fuse together because this they commute with this red node. So at the end, this correction here will exactly cancel all of this part. And then using the pi copy rules, and then this red node will basically be copied over these two elements, and so they will be cancelled with this correction here. So it means that at the end of this operation, then we will indeed get a single copy of our GZ state. But there is still one question: can we actually do this operation for any graph state? So are all graph states mergeable? And so the first contribution that we have is that indeed we show a generic map that takes any two copies of two graph states and obtain a single copy. So this part might actually make more sense to detail into this ZX seminar. So I will enter into more details here. But let me start with a short introduction to the scalable ZX calculus. So, why do I care about scalable ZX? Just because it's a tool that allows me to write this proof easily, and it was how I managed to obtain this proof. So, yeah, it's a very useful tool here. So in ZX calculus, you have like this usual generator, so like the green spider that are basically a superposition of ket zeros and ket ones with some phases alpha. Then you have this red spider that are also a superposition of plus and minus with some phases alpha as well. And then you have some other generator like this Adamor that we'll not use much here. Yeah, actually we use it at some point. We have the swap gate, that is what you expect. And then you have a Bell state here and a Bell projection, which is a projection against 0, 0 plus 1, 1. So here you can easily obtain a more standard gate. For instance, if you just have one input and one output here, then this object is basically a rotation around Z. If you have no input and one output, then it is ket plus if alpha is equal to 0, ket minus if alpha is equal to pi, and same ket 0, ket 1 if you use the red version. And then you can obtain a control Z by, it's what I draw on the first slide, by using basically two of these wires connected with a Adamor gate. All right, and what does scalable ZX brings? It brings you a way to represent in a concise form a collection of graph at the same time. So now wires are not just anymore like single wire like in the standard ZX, but you can have n wires that are grouped together in bold shape, and then you can group or ungroup these wires using this triangle symbol that basically does what you expect, which is just combine and ungroup wires. And then you also you can also represent spiders using in bold. Like now the alpha can also be a list of elements, and this is basically just a copy paste of the spider. So if this list has size n, then you can just take one spider with any element of this list and just put them next to each others. All right, and then you can do the same thing with the Adamor, so it's just a duplication of Adamor, and then you have basically the same rules applies also in the scalable version. So I will not use this one here, but they are here for completeness. And what will be extremely interesting in our case is also that we can represent via a matrix an operation. So this will this A is a binary matrix of size n times m, and so it will just send ket 0 to ket a of ket x, sorry, to ket of ax. So if this is a binary string, then this is again a binary string of size m. And it has some nice properties, like for instance, you can actually represent such matrix using this diagram, or this you have a connection between this node and this node if the corresponding entry in A is equal to 1. So intuitively this will copy and XOR the operation exactly like in a matrix operation. And then you have some operation to do block manipulation. So if you have a matrix that is in block, then it is actually equivalent to first copy the input and then apply the first matrix on the first copy and the second matrix on the second copy, exactly how you define this matrix multiplication. It's the same for a column, where you kind of sort the input and so on. And then you have some nice property in order to commute the elements. So here, for instance, if you have a green node on this pointy edge, then you can make it go through, it will commute, it will just take some matrix multiplication on this element. And for green, it flows nicely from right to left, and for red, it flows nicely from left to right. All right. So I will also give a few facts on graphs, how to represent graph state in scalable ZX. So there is a paper online that describes a very elegant way to represent graphs, which is just so this operation here just okay, sorry. I will denote by G the adjacency matrix of the graph G, and I will also cut it in two parts if the graph is cut in two parts, where A and B are just a partition of this graph, and then gamma will be the adjacency matrix of the graph connecting elements in A to elements in B. All right, and so ket G here, that will be defined like that, is nothing more than just applying a control Z between the qubits, the input qubits, whenever there is a 1 in the density trigonometric G. So here's this notation is just to mean that I only consider the lower triangle part of G. And then a graph set is just represented this way. And then you can easily prove also that you have some stabilizer properties that are true on your graph. And what will be handy in our proof is that you can represent any graph here, or you have n inputs, so you have n plus m outputs here because you want to split your graph in two parts. Then you can rewrite it like that, where you first intuitively prepare your subgraph A on the first part of your graph, then you prepare the second part of your graph, and then during a second step you connect these two parts by applying Control Z between the Control Z operation that are shared between A and B. All right, So now how do we use this in order to prove that any graph state is mergeable? So the first step is to use a Gaussian elimination by remarking that this gamma, so that will connect the elements between each others, can be written down like this. So first you apply some unitary U. Then based on the rank of your matrix, you will have identity on one side and then some arbitrary matrix RE here. And then you will have a bunch of zeros here, and then you will apply another vector V. So intuitively here, what we're trying to do is to kind of see where we can connect the two parts of the graph. So we will want intuitively to do bell pair measurement on this I here. And on that side, we will want to discard these elements, a bit like if you remember the GZ state example, we were doing one a bell measurement and a bunch of measurement in the Z basis. So here we will try to mimic this using this Gaussian decomposition. All right, and then my claim is that if we want to merge two states, then we want to apply this map here. So this will be the merging map, and this will be the correction map that you apply afterwards. And so this map, what is it doing exactly? So it is taking one copy, like one part of G, then it is undoing the control Z on this subpart of G. So we assume that G is cut into parts GM and the part GH. Then we will apply some Hadamard. Then we will apply, so V is what I defined right before, which is this part of the Gaussian elimination. So intuitively, we're trying to get rid of this part here. Then we will apply some Z measurement, and we will do something similar on the other qubit, except that this time we apply U. So intuitively, we are trying to get rid of this part here in order to access this identity wire around here. And then you will, and then you will apply a bell measurement on this identity part somehow, and we will apply some measurement in the computational basis for this second case and in the Hadamard basis for the first part. And then at the end, if we do the math, you can see that this will bring some correction that can flow and that will appear on this side using this more precise expression. And I will show you quickly how this can be done in ZX calculus. So here I will start from this graph, which is exactly what I drew before. And then I will use the fact that I can represent any graph G using, by first preparing a first subpart of the graph, another subpart of the graph, and then connecting these two graphs using control Z between H, the partition of H and the partition of M. So now if I just replace this definition inside my graph, then I get this new equivalent graph, and then I can do exactly the same on this second part of the graph G, which brings me to this new graph here. Then the next step will be to simplify that part, because here we have GM here, then we apply again this same control Z operation based on this matrix GM. So we can simplify them, because applying control Z twice gives you the identity. So in the paper we actually prove that this holds, but it is quite intuitive. And now we can again simplify this, because this is basically just identity. Then you have a bunch, two Hadamard, so they will cancel between each other, so you can remove them. And same here, you can again simplify this thing, because control Z applied twice will cancel. Then you have again the identity wire here, so you can simplify this. Now we want intuitively to merge this two operation in order to remove this D part. So you can prove that basically by definition of the Gaussian decomposition of gamma into U, V, and then a matrix based on identity, which is basically this wire here, R, which is basically this wire here, and 0, which is basically this wire here, then you can prove that this gamma is equal to this thing, and it is not complicated. You just use here the definition of how to split a block matrix into two submatrices, and you directly get to this expression. And now we can just replace the definition of this expression inside the circuit. So this brings us here. Now we're starting to see what I meant before, that we want to cancel this V. So here you have V and then the V minus 1, which are applied next to each other. So they will cancel between each others. Then here we have like some wires that you merge together and that you unfuse later. So you can again, so this is some basic rewiring that you can do in ZX, and then you just get basically a K0 that you measure on the Adamor basis. So it will just give you some scalar, so that we don't care here. And then we can do exactly the same replacement. So we replace the definition of gamma here. So here there is just a subtlety, because you can see that now it is pointing backward in a sense in this circuit. So you need to mirror this graph, but the same is true. And now the mirror of U will cancel the actual U, so you can remove this part. All right, and then again by doing some rewiring, we are back to this picture. And then if you check, before we said that basically the green part will nicely, sorry, the red nodes will nicely combine with the R node. So you can now basically just use the scalable rules in order to combine them in order to obtain this thing. All right, and now you can start to see that we are trying to push all the modification toward this wire until all the corrections are applied on this side here. So let's forget about this box here. All right, and then now the next step is to kind of make this part flow to this direction. So here you can see that the red correction are not too hard to make it commute here, because this is a red white wire, so we can make it go on this way. And here we can see why it's important to have done this Gaussian elimination, because the red does not commute nicely when it enters this R block. So if you try to, like, if the red part was going on this side, it would be impossible to make it flow on this side. So that's why here it was important to have identity on one side and a matrix R on the other side. And now because this U is actually invertible, so you can actually in that specific case it commutes nicely, because you can just invert this part. So you just get U minus 1 here. All right, and now we'll do the same thing, like moving this green part again. So now, due to the fact that we have, like, due to the pi copy rules, and this will just flip. But now, remember, we said that green can flow nicely through R, so we will get to this picture here, except that we have this R that will be applied. And now we will just fuse this operation, so they will just combine into a larger vector, because we just combine these together by concatenating them. And then again, because this part is invertible, then we can make it flow nicely. And now the last part is basically to combine everything here. So the green part will just flow here, and now we have exactly the same thing before and after, so we can cancel this part. So we are just left with the remaining part that is basically just made so that it works. All right, so now because we have a green, we can push it here. So intuitively we'll try to have a stabilizer part here. And now the problem is that the red doesn't commute nicely with this thing, because it will copy again. So if we push this X, so actually this X is defined to be exactly this thing, so that they cancel. We choose the correction exactly for this purpose. So because of the definition of X, we can cancel these two parts. And so we are back to this picture. And now we can see that this part is exactly a stabilizer. So that's why it's important to have a graph state. It's because of this part mostly. And so we can just remove this part altogether. And then you can see that this part is just basically the definition of gamma. So you can remove it, just replace it with gamma, and so on. And now this is basically just the definition of G. So it means that we are back to we wanted to prove, that this graph is exactly equivalent to G. And here you can see that it's actually quite helpful to have a scalable ZX, because it really helps me like to see how to wire things together. And the proof is very generic, and I think, yeah, quite easier to approach this way. So great. So now we prove that all graph states are mergeable. So remember, we started from the property of being mergeable just in order to be able to just be correct. Like if the distinguisher is just honest, then we at least need the state to be mergeable. But what is actually surprising is that being mergeable is not only necessary, but it is also sufficient for security. And then in the article, we actually prove that if for any state that is mergeable, so also for any graph state, then we can define a simulator. So this is basically the shape of the simulator that we define in order to prove the security of the framework. So here the simulator will be actually quite natural. So they will just run the honest protocol. Then at the end, they will get some quantum state. Unless you abort, then you will apply this merging operation that I just described. So intuitively from this side, you will get, one part of the digital state. So you want to fuse that part of the digital state with this other graph state, sorry. And then at the end of this merging operation, then you will apply the corrections that will be defined by X, and if these corrections are valid, which is always the case because we choose F so that this is always true, then at the end you will just output this state. And then you can actually prove that this distinguisher is correct. So in order to do that, we basically prove that if there exists a distinguisher that can distinguish this from the real world, then we can actually break the security, the game-based security of the original graph state verification protocol. So one might wonder, why do we add this function f that needs to check if the correction are allowed? So this is actually important because otherwise the adversary might do very crazy, the adversary might do any operation or any correction they want. Like for instance, if you want to prepare a digital state, but you allow the adversary to apply a different X correction on any state, then of course the adversary can just do things that you don't want. For instance, if you want to use this digital state to do a coin flipping protocol, then you will expect in a true protocol that all parties must share the same outcome. And here, if the adversary can send some correction, then the outcome might be different between players. So that's why you don't want to allow any arbitrary f. And our claim is that the set of state that we allow is actually doesn't harm the security in any way, and because it is actually a subset of the stabilizer of the state. So it means that intuitively what we do right now is that we ask the functionality to apply, for instance, on the bell pair, some rotation around A and some rotation around B. But in fact, the adversary could also just start from a bell pair and apply this rotation on their side, and then it will basically teleport to applying them on the other side. So in a sense, it would have been possible to, it's possible already for the adversary to do this operation, except that because of timing issue, yeah, never mind. All right, and in practice, we can see exactly the same thing, except that you have a generic stabilizer here, and so saying that you apply one part of the stabilizer on one side is the same thing as applying the other part of the stabilizer on the other side, and they will just cancel between each other. All right, so one might wonder, okay, if the adversary can apply the correction, why do we need to tell the functionality to apply this correction? Why can't the adversary directly apply them? And then we prove actually that it is possible to tell them to tell the adversary to apply this operation intuitively by applying no correction at all on the size of the functionality. And in order to do that, we need to apply one more run of the protocol. So it means that you need, of course, to change a bit the protocol, because if it's just black box, then maybe all communication are encrypted, and the simulator has just no way to change them. So we need to add another runs in the protocol, where you ask all parties to apply a random stabilizer. And intuitively, this helps because if the distinguisher cannot tell if the stabilizer is applied by the honest party in the true protocol, or if the stabilizer comes from the fact that there are some correction that applied due to the merging operation and that were not corrected, and that end up being sent to the party. Yes, so I can now conclude by saying that we prove that all graph state verification protocol can be turned into a composably secure protocol with the standard functionality using this last trick that I just presented. If you don't want to change the protocol and it is still secure, but then you will need to live with the fact that the functionality is a bit less standard because it accepts some subset of correction from the adversary. We also prove that it is optimal in the sense that we need at least to change the protocol or the functionality. In our work, we actually generalize the notion of entanglement swapping to arbitrary graph states using scalable ZX calculus. And I've not presented that, but in the paper we also study existing protocols in order to prove that existing protocols basically fulfill the requirements of our protocol, which is quite standard. I just want to put a small warning, like if the protocol that you consider from the very beginning is polynomially secure in the game-based security framework, then it is still composable with a polynomial epsilon, which might not be which might not be as secure as you hope from a composable framework. But if you start with a protocol that is exponentially secure, then there is, our construction preserves this, and so the composability will still hold with exponentially small epsilon. There are a bunch of open questions still. So can we generalize to other states, like continuous variable states, states that are not directly graph states, because you might want to generate other kind of states in the protocol, and Q-treat and so on. And I'm also curious to see if there are other applications for our generalized entanglement swapping proof, and more generally try to see if other verification protocol fits in our framework. So I'm arriving to the end of my talks. Thanks for your attention, and please feel free to ask any question.
Okay, thanks, Leo. Thanks for the talk. People can use the clapping emoji thing in Zoom and show their gratitude. Do we have any questions from the audience? Okay, well, let me ask a maybe obvious. Oh, I see a call. There's a hand raised.
Yeah, this is like a question, but also partly a remark related to your future work on your final slide. Where you have these I think this would be easier to do for Q-trits or CV, because when you have these graphs for Q-trits and CV, you can like merge them into the phase in the scalable ZS calculus, which may make your calculations easier.
Why is the case that it would be simpler, you think, with Q?
So like if you go back to your slide where you're like doing the simplification, this big like yeah, like here, like if you like G of H, you can like using the scalable ZX calculus for odd dimensions, or for CV, you can like pull the G of H kind of into the spider in a sense. So you don't have to like have so that the commutation and stuff just comes from spider fusion and stuff. So it may be, the calculations may be easier.
And then, because do you have a notion, because here it's also important, like to kind of be able to decompose the state into, like we have this Gaussian, like for
Yeah,
instance, how do you define this matrix A in for Q treats? I've not
matrix
tried
A.
it. Yeah, because
What's A?
in the case of, so I mean, like, okay, like this V here, for instance, when you have a matrix, because okay, let me try. Yeah, so here, for instance, I want to say that I can define my gamma here in like this Gaussian decomposition, and then how do you define this gamma here, like for generic Q treats? Because in that case, it's not a binary matrix anymore, I guess. So it will be like a Q treat matrix.
It'll just be a matrix over the integers mod 3.
Okay, and then it works the same.
But specifically this decomposition where you like pull the graph into like 2 different spiders with the matrix error in between, then that's you can kind of see this as you start with your G on the left as like a spider where the label is G in the spider, and then you kind of pull the spider into 2. So it's just you don't have to like have these boxes in the Q trait case, whereas in just complications for qubits. But I'm just saying it's hopeful. Yeah.
Then, and intuitively, do you know why? I mean, why intuitively it will be? I mean,
Because the problem is with qubits graph states, you can't have on the diagonal. You can't have anything, because there's this problem with mod 4 versus mod 2 for qubits.
Okay, interesting. Okay, thanks. Maybe you can.
Leo, I have a question. Thank you very much for the talk. I wonder, during the animation, you mentioned like the adversary want to do some correction. Like how do you confirm that the verification of the protocol like does not need to consider the noises? Like how do you distinguish between the correction that is needed from and like the noises that is propagated in the system?
So like in the security proof, I just consider like a noiseless. I mean, I have no notion of noise in the reduction proof. So in practice, if you have some noise, it will be considered as like adversarial manipulation of the state. So if you produce, for instance, a state that is not exactly the one you expect, then it will lead to an abort maybe in the original protocol. So I mean, if you have some noise, it will be just considered as an adversary that is doing something slightly different from the protocol. So the noise is already built into this framework by just saying the adversary is, instead of being fully malicious, is kind of honestly behaving, but with a bit of noise. So you will have more abort maybe, or that kind of things. But the correction that we apply inside so like the correction that we have here, for instance, they are very different. They are not due to noise or anything like that. They are just due to the fact that we want to apply this merging operation, and that it will you need to correct the fact that you have this non-deterministic outcome somehow. So it is kind of very different than a correction that you will have because of the noise. So this will be directly built into the protocol itself.
And can you show an example in the anime where you have the abortion?
An example in the what?
In the animation, like did you show us there's an abortion? Like I forgot, what does it look like?
Like you mean this animation, or?
And like the one that you verify the protocol, like was there like an example of abortion?
So I kind of put abortion under the hood in this presentation, but so here, for instance, if you have a protocol here, then at the end of the protocol, so the simulator will basically run this the honest protocol that you will get. So now let's say that the distinguisher or that the source is a bit noisy. So in that case, these parties, they will sometimes they will get what you expect after the measurement. They will get like a digital state, but if the noise is a bit too high, sometimes they might have an abort. So this is not introduced by us is just inside the protocol that there is like, I mean, depending on the protocol, it might be computed in different way, but in existing protocols, usually they test many states, and then if sometimes the measurement isn't the one you expect, you just say, oh, the source was malicious, or so I will abort the protocol from now on. And so at that step, then you will have an abort bit. So it means that one of the party will have an abort bit. So actually, we expect all the parties to have this abort bit. So in the protocol, in the paper, we actually assume that there exists a public channel in order to tell to all parties that we abort it. And if a single party abort it, then all parties will abort at the same time. And then the simulator will just pick this bit. They will realize that an abort occurred, and then they will tell to the resource here. So inside the resource, there is actually another. So the first message that this resource will receive is, are we gonna be honest or not? And then are we gonna abort or not? And then if you abort, then it will send abort to all honest parties.
Oh, so all parties will simultaneously be informed that there is an abortion.
Yes, exactly. So this resource will make sure that whenever whenever the simulator sends a message to this box, then all parties will abort in this scenario.
Oh, and another thing is, I've never seen any presentation like this before. Like, I was curious how you made that animation. Like, did you record it, or was it done in the PPTX? Like, how did you make it so, like, magic?
Well, I use different things. So like I use here, for instance, I use Manim, which is like something that is made for 2D animation. Then sometimes I use Blender, but not today, except for the thank you at the very end, but it's not very visible. And then I have used Inkscape. Like for the ZX thing, I just use Inkscape. Then I pre-recorded. And then I made some custom LaTeX thing in order to automatically insert a video in a LaTeX presentation, add some stops. And then I created a player to play the video and stop at the right time. You can actually find the web version online. If you're interested, you just send a video with some stop points and it will stop at the right time.
You can insert video in LaTeX?
Yes.
Nice.
I don't know if I have the source. It looks like this. Like I just say like, so this is just a Beamer presentation with some regular slides, and some of them are like this. And then I say, yes, like include this video from here, and then stop at these steps. And then I made some stuff under the hood that will compile to video with stops and stuff.
This must be a lot of work.
I did that a while ago, but during my PhD, but it's still useful.
So I have a question. So this shows you can merge all graph states with this definition, but like it looks to me like this method should also work for any stabilizer state, right? Since any stabilizer state is a graph state of local Cliffords, and those local Cliffords, they shouldn't really affect anything. Like they might change the basis in which you want to do measurements.
Yeah. Yeah, to be honest, I've not looked at stabilizer just because I'm not. I mean, yeah, graph state. Yeah, I mostly know graph state, and I don't work a lot with stabilizer directly. But yeah, so if you just start from a graph state and then just apply some local operation, then you can even directly run the protocol on the graph state itself and then apply the local operation later on. So it's not
right. Yeah. Yeah. So the distributed part doesn't even have to care about the local Cliffords because that can just be done locally. Yeah.
Actually, if you look at the paper online, sometimes they say, oh, like we want a protocol for digit states, but then in practice we only have it's easier to work with graph state. So we define a protocol for something that is locally equivalent to a digit state, and then at the very end, so usually you apply a local operation to turn it back into a stabilizer state. But yes, in this case, it's not. I mean, It's easier to work with graph state directly, but maybe you don't even need to do that, and maybe you can directly apply the protocol stabilizer. I don't think it will be really fundamentally different at the end.
And so if I understand, so the main result correctly, you're saying that if you have a secure protocol for distributing a graph state, then this is also composably secure. Is that sort of the correct way to interpret this result?
Can you say again?
So that are you saying like sort of all graph state protocols are composably secure, but should I interpret this like if I already have a protocol that distributes a graph state, then this will also be composably secure. So I first have to show security of the protocol, and then once I have that,
Yes.
this sort of generic algorithm of yours sort of shows you it's also composably secure.
Yes, exactly. So I've not given explicitly what I mean by a protocol is secure, but so it is secure in the game-based model. It's everything I say, but it's basically what you expect in the sense that at the end of the protocol, you should be in trace distance. So even if you have malicious parties, you should be basically the state you obtain at the end should be close in trace distance to the target graph state that you want to produce. And then this closeness is basically the epsilon, and then you will carry on this epsilon to the because in practice usually you're not exactly indistinguishable, you're indistinguishable up to epsilon, and then the epsilon that you obtain from this trace is polynomially related to the epsilon you will get at the end in the composable proof. But yeah, you need to start from your protocol, and then you prove the security in the game base, and then you use our compiler somehow to prove that it's composably secure.
So this epsilon doesn't play a role in your proof, like with the rewriting? I mean, it's all exact rewriting, but then like conclusion is like if you start with something epsilon close, you get something epsilon close.
Yeah, so the epsilon in the proof, so it's not directly visible here because so here I already assume that this graph here is a perfect graph and that this graph here is a perfect graph. But in practice, if for instance your protocol is epsilon correct, then you will not have exactly a graph G, you will have something that is epsilon close to graph G. And then how the proof goes is that I say, I define like a series of hybrid games. And then in the first hybrid games, I say, first, we can replace, so we can cut the distinguisher in two parts, one before the preparation of the state, one after. And then I kind of change this part. I mean, I say it's not possible to see if you use actually G or like the state that is epsilon close to G. And in that step, I lose epsilon depending on how close they are. And then once I arrive here, indeed, this part is exactly equivalent. So I don't lose anything in this merging step. But where I lose is when I say that the state that I obtain is epsilon close to a graph state. So if I replace it, then it is not visible to the adversary.
Do you have any other questions from the audience?
Can I ask another one? So you mentioned about your proving composability from 3 models, and how is the sequential model different from the game-based model?
So that's a good question. So in the game-based, in the, do I have the, okay, maybe I can. So here in this picture, you have a distinguisher, and this distinguisher is allowed to interact. So this is why intuitively it's generally composable in the sense that you can do things in parallel because here the distinguisher is not, I mean, they can do anything in parallel and then send messages, receive, do something else. So that's general composability. In sequential composability, you are only allowed to compose protocol one after the other. And in that case, you change your definition by saying that the distinguisher is kind of in 2 parts. One part where they provide the inputs to this adversary. Then a second part where they will get the output, and you add another what we call an adversary also. So this adversary is kind of playing the thing in between. So you kind of cut your distinguisher into 3 parts before in between and after. And due to this structure, you are only then able to prove security when you compose things one after the other, because
The order.
yeah, because you cut this distinguisher in two parts, and so the distinguisher is not anymore allowed to do something else during the protocol. They can only do something else before the protocol or do something else after, but not do something else during the protocol.
And how about a game-based one?
So in the game base, it's even different in the sense that you don't have even this notion of ideal resource that models like what you should be allowed to do in game-based setting. It's more like you will prove that at the end of the protocol, no adversary can distinguish this from that. So usually you have a set of properties that you list, and then you prove that these properties are fulfilled, but it doesn't mean, I mean, it's not really modular. Like you just prove one specific property. Like it's not possible to distinguish this transcript from this other, or like it's, I mean, it's not possible to forge a new signature, or it's not possible. Usually you have like a bunch of properties, but they are saying just some generic properties on what the adversary cannot do, but it's not saying everything that the adversary is not able to do. It's just like kind of listing a few things that are impossible for the adversary. While in this framework, it's most like you list everything that the adversary is not able to do. Like, so in a sense, that's why it's a bit more powerful, because this resource here really quantifies all the possible attacks that an adversary is supposed to be unable to do, and then you don't really need to list like to give a list of attacks.